Good morning, everyone. Today is our last lecture content for the semester, the topic being environmental stress. A couple of quick announcements as always. Just a friendly reminder, your case study number 2 is due this Friday, March 27th by 11:55 in the Dropbox on Sakai. Preferentially, this assignment, please submit it as a Word document or a .docx or a .doc file. Please and thank you. As I mentioned previously, this is the last lecture content for the semester, so topic environmental stress. The last lecture capture will just be a final exam review. Please note that the poll on Sakai is open for the final exam date. I'm waiting on a couple of votes from a couple of people. It'll be a 48-hour take-home exam format, and right now it looks like it'll be April 13th to 15th. Lastly, course evaluations open on March 27th. I'll send you guys an email with a link to that. Again, please take the time to vote on this or to answer some questions on this, as it's really important to me that I can improve for future teaching opportunities. So today's lecture, as always, an introduction to the topic, so environmental stress. We'll then move into a number of different environmental stressors, being heat, cold, altitude, pollution, outer space or gravity, and lastly, circadian rhythms. So just an introduction to the different environmental stresses that we'll come across and a broad overview of the topic in general. So environmental stress, it's the influence of the environment on physiological and metabolic function. Environmental factors, again, that we'll touch on are different temperatures, different oxygen concentrations, air quality, gravity, and circadian rhythms. Note that these can be acute exposures or chronic adaptations to these environments. And another key point that we're going to have to think about is something called thermoregulation. So you guys will have seen this in 3P90, but really it's our body's ability to respond to these different stressors and our ability to maintain a neutral, about 37 degrees C core temperature when exposed to these environments. So quick background on the history of environmental stress, environmental research. Most of the physiology and metabolism work that started this field emerged out of the Second World War. This was really used as a tool to help soldiers outperform their enemies in extreme environments, so really benefiting the military system. Now, environmental research or environmental stress-related research can apply to workers or even athletes. So when we think of workers, we're thinking of groups like miners, mountaineers, military personnel, astronauts, or firefighters. When we think about athletes, we could think about the Summer Olympics in a hot environment, we could think about the Winter Olympics in a cold environment, or even athletes that perform at altitude like climbers. Interestingly, most of the metabolic work in this field is relatively new, specifically within the last decade or two. So how exactly do we study environmental science? Two main ways. The first, in a more controlled setting, we have something called an environmental chamber. So that first image on the top there is an environmental chamber. It's literally a box or a room that we can manipulate temperature, humidity, or oxygen content. And what we do is we can actually study participants and their physiology or metabolic responses within a fixed and controlled environment within a laboratory setting. Secondly, we can also do field studies. So looking at workers and athletes in a real world setting, we can follow them and investigate their different physiologic and metabolic responses to an environment. So for example, we could follow a mountaineer up Mount Everest. We could study a firefighter in a simulated or a controlled burn setting. Or we can even look at miners and how their bodies respond to being closer to that core of the earth. So the first thing I want to talk about and the first environmental stress we'll look at is heat exposure. Specifically, we'll focus on acute heat stress to start with. So when I think about acute heat stress, I think about this picture here. It's kind of frustrating, it's stressful for the system, and we're going to figure out how exactly it influences skeletal muscle metabolism and athletic performance. So you guys, again, will have seen this in 3P90, but heat exposure or heat stress is an environmental stress that can increase core temperature. So our physiological responses to heat stress are increased core temperature, increased sweat rates to try and minimize that increase in core temperature. And really the potential risks that we see are hyperthermia, so again, that elevated core temperature. Because we're sweating more, we might have a decreased blood volume. Decreased blood volume can influence cardiac output if there's less blood to pump around, and that will typically manifest with a decrease in stroke volume. Moreover, more specific to muscle or skeletal muscle is an increase in muscle temperature that is seen with acute heat stress. And really, again, as you know, for the purposes of our class, we'll be focusing on how this acute heat stress can influence skeletal muscle metabolism. Another factor we need to consider is whether humidity can influence our ability to thermoregulate. So what humidity really is the water content in the air that we're surrounding ourselves with. We can have dry hot or we can have wet hot conditions. So dry hot is minimal humidity. And because in dry hot conditions, what it's characterized by is the ability to have this evaporative cooling. So we sweat, it is soaked up into the atmosphere. Wet hot is high humidity. And because of that high humidity, when we sweat, it pools on our skin's surface and the evaporative cooling response cannot occur. Because of that, this results in more rapid rises in core temperature and can be a greater physiological strain on our system. So the first thing I want to look at with acute heat stress is this idea of how it influences maximal oxygen uptake. So this study looked at 13 male soldiers. What they did was they performed a VO2 max test in a thermoneutral environment, so 21 degrees C, 30% humidity, fairly normal, as well as a hot environment, 49 degrees C, 20% humidity. So low humidity, but hot conditions. And what they found, if we look at this table on the right here, so moderate is that thermoneutral environment, hot is obviously the hot environment, we see that VO2 max is significantly lower in the hot condition compared to the moderate or the thermoneutral environment. This is actually about an 8% reduction in VO2 max when we exercise in that hot environment. So there's a significant impairment in exercise capacity. But now we need to delve into this idea of why might there be an impairment in aerobic exercise performance in the heat. So the first thing I want to come and look at is muscle lactate accumulation. So what this study did was it wanted to look at muscle lactate accumulation in 13 males in response to hot and cool environments. So they did 30 minutes of cycling at 70% VO2 max, so a high aerobic intensity exercise. Again, the cool environment was 21 degrees C, 30% humidity. The hot environment, 49 degrees C with low humidity of 20%. They took muscle biopsies before and after the exercise to determine changes in muscle lactate concentrations. What they found here is that exercise in a hot environment resulted in significantly elevated muscle lactate following submaximal exercise. This was a lot higher than in the cool condition. And what's interesting is they also found a significant increase in muscle lactate, which was higher in the hot condition, in plasma lactate, which was also significantly higher in the hot condition compared to the cool. So if we look at this figure on the right-hand side here, what we see is that the hashed lines are post-exercise. So we see this dramatic rise in muscle lactate regardless of in a cool or hot condition following the exercise bout, but that rise was dramatically higher in the hot condition compared to the cool. Importantly, pre-exercise muscle lactate was not different between the two groups. And again, this is only showing muscle lactate concentrations, but the same trend was seen for plasma lactate. So the next thing we want to consider, so we've seen these differences in muscle lactate concentrations following exercise in the heat. What about muscle glycogen? So what this study looked at was 6 endurance trained males, and what they found was that looking at prior to exercise, one leg was actually cooled. So they had this suit around the body, running cool water through it, 0 degrees C, and the other leg had warm water running through it, about 55 degrees C. And this was done for 40 minutes prior to that exercise bout. They also continued to run these different water temperatures over the legs for the exercise bout as well. Their control check to show that one was a hot condition and one was a cool condition was measuring muscle temperature. They also took muscle biopsies prior to and following the exercise bout. And what they found, so comparing rest and post-exercise in the cool and hot conditions, at rest, there was absolutely no difference in muscle glycogen concentrations, which is good control check. But what they found is that following exercise with the hot condition, muscle glycogen utilization was significantly greater than in the cool condition, meaning that when muscle temperature rises, muscle glycogen breakdown rises as well. So the question really becomes, can we minimize these metabolic disturbances? Is there something that we can do to combat these acute heat stress scenarios and to preserve muscle glycogen or prevent these rises in muscle lactate, as we know they contribute to fatigue? So the first scenario we look at is something called pre-cooling. So what pre-cooling is exactly what it sounds like, cooling prior to exercise. This study took 8 healthy, non-heat acclimated males, and they put them through 3 different scenarios. In the first scenario, they ingested 7.5 grams per kg warm fluids. This was the same temperature as core temperature, so 37 degrees C. In another condition, they ingested 7.5 grams per kg of an ice slurry mixture, so a cold fluid. Or, in the third condition, they had themselves immersed in cold water prior to exercise. What they did was they did a submaximal run to exhaustion in a warm 34 degrees C and high humidity 52% condition. What they found was that both cooling scenarios, whether it was the ice slurry drink or the cold water immersion prior to exercise, significantly allowed for greater time to exhaustion compared to ingesting the warm fluid. The greater time to exhaustion was also accompanied by lower core temperature changes, as well as decreased perceived exertion, lower heart rate, and lower thermal stress or thermal sensations, so how hot they actually thought they were. Another strategy is something called percooling. So percooling is actually cooling during exercise. So what this study looked at was 7 healthy males who were either in a scenario where they're in a control condition with no ice vest, or they exercised with an ice vest on. It was put on after 30 minutes of cycling, and what they actually did was exercising in a warm 30 degrees C and humid 40% humidity condition. They did 10-minute cycles of 9 minutes of submaximal exercise followed by a 1-minute sprint. They repeated this effort until exhaustion, and what they found was that wearing the ice vest contributed to a significantly greater time to exhaustion, and this was about 13 minutes longer than in the control condition, likely because it maintained a lower core temperature, lower perceived effort, lower heart rate, and things that would allow us to exercise for longer periods of time. So the next idea I want to talk about is, up until this point, we've discussed acute heat stress, but what about acclimation to a hot environment? How does that influence skeletal muscle metabolism and athletic performance? So can we expose ourselves to heat regularly to minimize its negative effects on our physiology and metabolism? So how do we actually go about heat acclimation? So first of all, I want to address the difference between acclimation and acclimatization. Acclimation is heat stress in a controlled environment. So think about anything we would do in a laboratory where we expose you for a fixed amount of time, a fixed number of days, a fixed temperature, and a fixed humidity. That's acclimation. whereas acclimatization is heat stress in a natural environment. So every summer we become acclimatized to our environment of our Canadian summers and our Canadian winters as well. So heat acclimation protocols typically take 7 to 14 days, and the daily exposure ranges vastly. That's why I have that asterisk there. On average, it's about 1 to 2 hours, but it really depends on whether it's standalone or following an exercise bout. In that case, it can range from 30 minutes following an exercise bout to 4 hours on its own. When we talk about heat acclimation, a lot of the physiological adaptations we see are reduced core temperature, reduced heart rate, reduced ratings of perceived exertion, increased sweating, and improved exercise performance. We're going to discuss really honing in on, again, the skeletal muscle side of things. But when we talk about heat acclimation, the way that it's commonly achieved are through sauna exposure or hot water immersion, which is a fancy term for a hot tub. But those are the main methodologies that we'll see for heat acclimation protocols. So how does heat acclimation influence substrate utilization? Here we see 8 active males, and what they did was they performed an exercise test, 60 minutes at a low to moderate intensity, 50% of a VO2 max, prior to and following a heat acclimation protocol, which involved cycling at 50% of their VO2 max for 90 minutes a day over an 8-day period. So every single day they did that for 8 days, and that was done in a hot environment, 40 degrees C, and their exercise tests were also performed in a hot environment of 40 degrees C. If we look at the figure on the top, what we see is that following the acclimation, so pre and post acclimation is what we're looking at, muscle glycogen on our y-axis, its utilization during that exercise bout was significantly decreased following heat acclimation, meaning they used more muscle glycogen during exercise prior to acclimation than following acclimation. Moreover, what they found, highlighted in the red box there, is that there was a significant reduction in carbohydrate utilization or carbohydrate oxidation following acclimation, with a concomitant increase in fat oxidation following heat acclimation. So less carb used, more fat used for the same exercise intensity, only because we have acclimatized or acclimated ourselves to the hot environment. So that's great that we see changes in substrate utilization, but what about actual exercise performance, the thing that matters for athletes? So this study looked at 20 highly trained endurance cyclists. 12 were heat acclimated and 8 were a control group that were not acclimated. Their tests were performed in a hot environment, so 38 degrees, 30% humidity, or they were performed in a cool environment, 13 degrees C with 30% humidity. They did 2 tests. One was a VO2 max test, and one was a 60-minute time trial to see how much work they could complete. Their heat acclimation protocol involved 10 exposures, involving exercise in a 40 degrees C, 30% humidity. And how they did this was every time they would do 2 bouts, so 45 minutes at 50% VO2 peak, 10-minute rest, and another bout of 45 minutes at 50% VO2 peak. What they found, so if we look at the top panel, panel A, it's looking at VO2 max in relative terms. We see that following acclimation, so in the white bars, even in the cool environment, we see that heat acclimation results in improved VO2 max for both the cool environment and the hot environment. Moreover, when we look at panel B, what we see in the experimental group, so the group on the left-hand side, is that the amount of work completed during that time trial was significantly improved following acclimation in the cool environment as well as the hot environment. So what we see here is that heat acclimation improves athletic performance, so aerobic exercise capacity. So we see the improvements in fuel utilization, but we also see improvements in exercise performance. And what's really cool about these findings, and I've highlighted that with the asterisks there, is that performance is improved in both hot and cool environments following acclimation. So really what this means is that heat acclimation might serve a benefit for exercise even in thermoneutral or cool environments. So it's not only beneficial for just performance in hot environments itself. Now the question comes, how long are you acclimated for? So we've undergone this heat acclimation protocol. How long am I good for until I'm no longer acclimated? This is something called the heat acclimation decay, or HAD. It describes the rate at which physiological adaptations disappear following heat acclimation. For every day of heat acclimation decay, what we see is that we see a decrease in exercising heart rate, which decreases by 2.3% every day that we are no longer heat acclimating. We also see an adaptation is that there's a reduced exercising core temperature. That disappears at 2.6% per each day of not heat acclimating. And there's no defined value, but research has shown that the adaptations to sweat rate seem to last longer than these other adaptations like heart rate and core temperature. The general rule of thumb is that for each day of heat acclimation that we lose, for each 1 day of heat acclimation is lost following 2 days of heat acclimation decay. So it's about half for each day of decay. Interestingly, what we also find is that if we undergo heat acclimation decay, so we're no longer heat acclimating, we actually find that heat reacclimation, so if we kind of pick up our routine again, it's about 8 to 12% or 8 to 12 times faster than the heat acclimation decay at inducing adaptations to heart rate and core temperature. So we can actually reverse these effects by just starting up our heat acclimation protocol again. So now we're going to turn away from heat exposure and really focus on cold exposure. So really flipping the coin here. Cold exposure is an environmental stress that can decrease core temperature. The typical physiological responses are increased heat production through shivering or non-shivering thermogenesis, and we'll talk about that on the next slide. But really the potential risks of cold exposure are hypothermia, frostbite or other cold injuries, and even shock. So when we talk about shivering versus non-shivering thermogenesis, in the context of skeletal muscle metabolism, we're really going to be focusing on shivering thermogenesis, so how our skeletal muscle contracts in order to generate heat through ATP breakdown. But on the other side of the picture, we think about non-shivering thermogenesis. We can also think about heat production due to metabolic processes not involving skeletal muscle contraction, so thinking about mitochondrial uncoupling proteins or UCP3 specifically in skeletal muscle, or even brown adipose tissue or BAT, which we have seen before. So this study in 1992 by Bell et al. Looked at the shivering patterns of humans exposed to a cold environment. So 10 male volunteers exposed to 10 degrees C air for 2 hours. That doesn't sound so bad, but trust me, that's pretty cold. And what they did was they recorded EMG, so electromyography, of 6 muscle groups: the chest, the abs, the calf, the bicep, the quad, and the forearm, so major muscle groups. And what they did was they determined shivering intensity relative to maximum voluntary contractions and looked at how different muscles were recruited during that shivering or cold exposure. And what they found was that shivering intensity was highest in the central muscles, so the muscles closest to the core, whether that was the chest or the abs. And these intensity of the shivering equaled about 5 to 16% of the maximum voluntary contraction. So that's pretty intense shivering. And probably without surprise, because those muscles, those central core muscles, had the highest shivering intensity, they were responsible for 71% of heat production from those skeletal muscles measured. 21% also came from the quadriceps, and 8% came from the remaining muscles, so the calf, the bicep, and the forearm. So basically, the larger the muscle group, the more shivering you'll see, and the closer to the core, the more shivering we'll see, and those generate the most heat because We know shivering is skeletal muscle contraction, breaking down ATP, generating heat. So what this study did was now shifting towards non-shivering thermogenesis. We see rats previously housed in a neutral environment were now taken and exposed to a cold 5 degrees C environment for 24 hours. And what happened was the 24-hour cold exposure resulted in basically a threefold increase in uncoupling protein content in skeletal muscle. So that's what that figure is on the right there, just showing you in the black bars that cold exposure results in this dramatic rise in UCP3 protein content. Other interesting things that they found was that there was a lowering of the mitochondrial membrane potential and sensitization of the mitochondria to uncoupling, meaning that they were more likely to produce this uncoupling in response to the cold. Taken together, all that really means is that mitochondrial uncoupling may be a means for metabolic heat production during prolonged cold exposure, at least in rodents. And the last angle I really want to talk about here is brown adipose tissue, or BAT. So this is actually a study in humans, and it was the first study in humans to look at brown adipose tissue. 6 healthy men, what they did was they exposed them to a neutral room and then a condition where they were immersed in 18 degrees C water, so cold water. And what they did was they took PET scans to look at cold-induced activation of brown adipose tissue. And really what we're looking at here is a top-down view of basically the neck region. And in this image, what we can see is those dark spots is brown adipose tissue. So brown adipose tissue is typically found right around the neck, the base of the neck, and it's actually thought to play a role in preserving brain temperature in response to the cold. Nonetheless, what they also found was that despite imaging this brown adipose tissue, they found in response to the cold environment, there was reductions in BAT triglyceride content, meaning that the brown adipose tissue was breaking down fat to create energy, and this was associated with an increase in total energy expenditure. So really taken together, this was the first evidence that brown adipose tissue is a tool for non-shivering thermogenesis in humans, and really only before this, it was only shown in rodent models. So now thinking about how substrate utilization might change in the cold, this study looked at 10 healthy males. What they did was they had them walking, so 60 minutes at 50% VO2 max, or running, so 70% VO2 max for an hour on a treadmill. They were either in a neutral environment, so 22 degrees C, that's pretty normal, or a cold environment, 0 degrees C. And what they found was an increased reliance on fat for fuel in the cold. Interestingly, there was no difference in plasma free fatty acids, suggesting, although they didn't measure it, a greater reliance on intramuscular triglycerides during cold exposure. So what we're looking at on this figure here is the gray bars specifically. So we can see that walking in the cold compared to the neutral, we have an increased reliance on fat, or running in the cold versus the neutral, we have an increased reliance on fat. So those gray bars are higher in the cold environments for walking and running specifically. And what's more important too is that the effects are actually more prominent in the running compared to the walking condition. Of course, this is a greater metabolic stress, and it might seem likely that this is where you would see a greater difference. So of course, last thing we need to consider is exercise performance. So 8 males, what they did was they did a cycling task in a neutral environment, so 20 degrees C, or a really cold environment of negative 20 degrees C. And what they did was a submaximal time to exhaustion at an aerobic power output or intensity of 75% of their VO2 max. What they found was a dramatic reduction in time to exhaustion in the cold conditions, so 38% compared to neutral. And what they suggest is that it's possibly due to impaired muscle contractile function, probably due to a decrease in muscle temperature in this really cold environment. So decreased muscle temperature can impair our contractile properties, and impair our exercise capacity. So now shifting towards altitude and how altitude can influence skeletal muscle metabolism and athletic performance. So the first thing I want to talk about is just contextualizing altitude and hypoxia. So remember that when we talk about altitude, we need to consider the partial pressure of oxygen, where the partial pressure of oxygen is the percentage of oxygen times the atmospheric pressure. Importantly, you guys learned prior that percentage of oxygen never changes. So at sea level, it's 21%. On top of Mount Everest, it's 21%. What does change is the atmospheric pressure, meaning that at sea level, we have about 160 millimeters of mercury for our partial pressure of oxygen. But on top of Mount Everest, because our atmospheric pressure drops dramatically, we see a decrease in the partial pressure of oxygen. What's important about this is that oxygen is an essential substrate for mitochondrial ATP production, and we need oxygen to therefore facilitate aerobic metabolism. So just quickly, a little bit of fun facts, altitudes around the world. So we know Mount Everest is the highest peak in the world. It's about 9,000 meters above sea level. Acute altitude sickness can begin to appear about 2,000 meters above sea level. And there's evidence out there that suggests that most runners do not start to notice the effects of altitude until about 1,000 meters above sea level. So you can only imagine how dramatic the effects of Mount Everest would be for anyone trying to exercise, let alone summit the mountain. So the first thing I want to discuss before we talk about acclimation is what happens during acute exposure to altitude. So importantly, and for us, is this context of substrate utilization. So what this study did was looked at 8 trained sea level residents. So they did 2 experiments, one under normaxia at sea level and one under acute hypoxia where they simulated 4,100 meters above sea level. What they did was they cycled for 60 minutes at 50% VO2 max. This workload was determined at sea level VO2 max test. And really what we see here, and what I want you to know, is that they simulated altitude by breathing a low oxygen content. This is used by something called a Douglas bag. And what they did was they took blood samples at rest and every 15 minutes during the exercise bout. What they found was that there was increased carbohydrate oxidation, a reduction in fat oxidation to match this with acute hypoxia. Really highlighting the point that there's an impairment in the ability to rely on aerobic metabolism as soon as we have this acute hypoxic exposure. So the figure on the right here is just showing us the percentage of carb and fat utilized for this exercise bout. SL is sea level and AH is acute hypoxia. And what we see again is that there's this increased reliance on carbohydrates and a reduced reliance on fats. So now you're probably thinking, why might this be happening? A couple things that we can consider are basically this idea of reactive oxygen species. So what this study looked at was 9 volunteers. They performed exercise under acute hypoxia by taking a placebo or under acute hypoxia in the presence of antioxidants. They performed a single high-intensity exercise bout, so a Wingate 30-second all-out sprint. What they did was they took muscle biopsies prior to the exercise, immediately after, 30 minutes, and 120 minutes after the exercise bout. What they found, so the figure on the right here is showing us protein carbonylation. Remember, carbonylation is a measure of protein damage. What they found was that ingesting antioxidants prior to this exercise bout resulted in a decrease in protein damage or a decrease in protein carbonylation at the onset of exercise, at the end of exercise, at the 30-minute mark, as well as at the 120-minute mark following exercise. Importantly, and not shown here, is that this reduction in protein damage also coincided with a reduction in glycolytic rate, meaning that they used less carbohydrate for fuel and they performed the exact same on this Wingate. What we can really think about then is this idea that reactive oxygen species influence substrate utilization during high intensity exercise and hypoxia, but really, can we extend this to longer duration exercise and how this may contribute to earlier fatigue onset during hypoxic conditions for an acute exposure? Another angle we need to consider is what happens to mitochondrial function during acute hypoxic exposure. So this study was conducted in rodents, 4 conditions: control with a placebo, control with an antioxidant, hypoxia plus placebo, and hypoxia plus an antioxidant. What they found, long story short, so in this figure on the right, C is for control, P is for placebo, H is for hypoxia, and V is for antioxidant. So what they found is mice exposed to hypoxia and a placebo, so strictly exposed to hypoxia, they had greater reactive oxygen species. So remember that HSP60 is a marker of oxidative stress, i.e. reactive oxygen species. So when that bar is higher in the hypoxic plus placebo condition, we're seeing higher ROS formation. Importantly, this higher ROS formation translated to impaired mitochondrial respiration. Even more interestingly, when we look at the hypoxic plus antioxidants, so H plus V, what we see is that there's a reduction in these reactive oxygen species formed, and we see a reduction in the impairment to mitochondrial respiration, meaning that these reactive oxygen species are obviously a factor associated with hypoxia, and that this reactive oxygen species can obviously impair mitochondrial function. So really this idea that, taken together, acute hypoxia induces mitochondrial dysfunction through reactive oxygen species, and we can combat this through antioxidant exposure. So now I want to kind of change gears a little bit, think about resistance exercise. So not everything is related to endurance tasks or high intensity cycling bouts. And not everything is a negative associated with acute hypoxia. So what this study found was that looking at 12 healthy males, they had a condition of normoxia and acute hypoxia. What they did was a resistance exercise task, so 10 reps for 5 sets at 70% of the 1 rep max of bench press and leg press. And what they measured was blood measures of lactate, growth hormone, epinephrine, norepi, IGF-1, testosterone, and cortisol. Importantly, those are all markers for anabolic responses or anabolic hormone responses to resistance training. What they found was that in hypoxia, all of these anabolic markers increased to a greater extent. Perhaps then, resistance exercise in hypoxia is more beneficial for an anabolic stimulus. So now I want to take a step towards chronic hypoxia exposure, or adaptations that we might see with chronic altitude exposure, and how this might influence skeletal muscle metabolism and athletic performance. So what's important with chronic exposure to altitude is something called hypoxia-inducible factor 1, or HIF-1. HIF-1 is a transcription factor that responds to decreases in available oxygen, i.e. hypoxia, and HIF-1 is activated with this reduced oxygen content, and it's known to be the master regulator of a number of hypoxic-inducible genes. Some hypoxic-inducible genes that are going to be important for this class are increased activation of glycolytic genes. As we've seen with acute hypoxia, we see this increased reliance on glycolytic metabolism with hypoxic exposure. Moreover, we actually see an increase in the activation of vascular endothelial growth factor, or VEGF, meaning that with chronic hypoxic exposure, we see increase in vascularization in order to attempt to deliver more oxygen to our working skeletal muscles. So a chronic adaptation that we see with chronic hypoxic exposure is a reduction in mitochondrial content. So what this study did, really cool, was they followed 18 individuals summiting Mount Everest. They took muscle biopsies prior to departure and a few days after arriving at 5,300 feet or meters. And this is after it took them 66 days to get there. What they found was that there was a significant loss in mitochondrial density, so 21% reduction, and the remaining mitochondria actually appeared to be smaller as well. So the figure on the right here is showing you prior to departure in London, and then on the other side, the mitochondrial density at Everest. And what you can see is that really there's fewer mitochondria and the remaining mitochondria are smaller. What's important about this is that the actual localization of the mitochondrial losses were targeted towards the subsarcolemmal mitochondria. So we actually see a 14% loss of intermyofibrillar mitochondria. Remember that those are closer to the intramuscular triglycerides, meaning it's more important that we actually have more of those remaining. Whereas the majority of our loss of mitochondria actually falls into the subsarcolemmal, meaning that they are farther from the IMTGs and we're actually better to give those up. So it's actually cool that our body has the capacity to choose or preferentially select which mitochondria are sacrificed in response to this altitude adaptation. Another thing that's cool to look at is GLUT4 translocation. So what the study did was it was looking at C2C12 myoblasts, so muscle cells, and they were either a control or wild type or a HIF1 knockdown. And what they wanted to look at was insulin-stimulated glucose uptake into these cells, whether they were wild type or missing that or less of that HIF1 protein. What they found, so with the figure on the right here, we see at the top, insulin, so negative means without insulin, positive means with insulin, so insulin stimulated. In the wild type, we see that insulin-stimulated glucose uptake obviously increases in the presence of insulin. However, in the HIF1 knockdown animals, or in the HIF1 knockdown cells, we see that in the presence of insulin, there is no change or a very minor change in insulin-stimulated glucose uptake. So without HIF1, insulin-stimulated glucose is impaired. Moreover, if we shift to the figure at the bottom there, what we see is that we're looking at GLUT4 at the plasma membrane now. So in our wild types, we see this classic response where insulin causes an increase in GLUT4 at the plasma membrane, but in our HIF1 knockdown cells, there is no change in GLUT4 at the plasma membrane, meaning that there's some impairment in the insulin signaling cascade that's related to HIF1, and if we knock it down, there's an impairment in the ability to bring GLUT4 to that plasma membrane. What this really does is it suggests a link between HIF1 and glucose uptake, and possibly a link then to glucose utilization in states of hypoxia. So now I want to look at glycolytic enzymes. So previous research has demonstrated that under chronic hypoxia, muscle cells adapt to increase their reliance on glycolytic metabolism. And how this occurs is through an increased activity of all glycolytic enzymes. So I'm just going to take one enzyme as an example of this. So this is a cell culture study looking at PFK content and activity following chronic hypoxia. So remember, phosphofructokinase, or PFK, is the rate-limiting step for glycolysis. And what they found in this study was that there was a 2 times greater PFK content in chronic hypoxia, which was matched with a 2 times greater activity. However, what they found was that when they looked at specific activities, so the activity of PFK per enzyme present, that it was only a change in the PFK content that was contributing to this greater activity. It was not a greater activity per each enzyme present. So again, all of this attributed to a greater PFK content. So now let's think about what happens when we take someone who is traditionally at sea level, we expose them to hypoxia acutely, but then we keep them there for 7 days and let them adapt. So this study took 10 healthy recreationally active individuals, and what they did again was have them perform an exercise task at sea level in a controlled condition. acute hypoxia, so a one-time exposure to 4,300 meters above sea level, and then they kept them in a chronic hypoxic state for 7 days at that same altitude, so 4,300 meters above sea level. They had them perform an exercise task, which was 2 by 15 minutes of exercise, so one block of 15 minutes at 40% of their VO2 peak, and one block of 15 minutes at 70% of their VO2 peak. They then completed a time trial, which was to complete a fixed amount of work as quick as possible. What they found was that 7 days of hypoxic acclimation reduced the physical strain of submaximal exercise that was occurring with acute hypoxia. So really, if we look at this figure on the right here, we see time trial performance obviously was best at sea level. Acute hypoxia, that middle bar, significantly greater amount of time to complete that same task, so impaired time trial performance. But once they acclimated for 7 days, that post-acclimation is the last bar on the right, we see that the performance improved 16%, meaning that they had an adaptation to that altitude and they were able to perform better than when they first were exposed to that altitude. However, what's important to note is that their performance didn't improve to sea level performance measures. So they're still impaired compared to the sea level test. Just a quick note on how this might extend to disease. So a lot of diseases are actually characterized by a state of chronic hypoxia, so I just want to bring this to awareness. In the idea that there's impaired oxygen delivery to peripheral tissues. So just 3 main ones that I want to talk about are COPD, or chronic obstructive pulmonary disease, in which basically we have obstructive lung disease with poor airflow, meaning that we're taking in less oxygen and unable to deliver that oxygen to our skeletal muscle or our tissues of interest. Next would be congestive heart failure, otherwise commonly just known as heart failure, in which we have impaired ability to pump blood to our tissues of interest. If we have an impaired ability to pump the blood, reduced cardiac output, and we know that the blood carries oxygen, so impaired oxygen delivery. And lastly, peripheral artery disease, or PAD, is basically a narrowing of arteries in our body. If we have a narrowing of the arteries, there's impaired blood flow. If there's impaired flow, we also have impaired oxygen delivery. So all of these scenarios induce some kind of chronic hypoxia within the body, and therefore studying chronic hypoxia is important to extend our knowledge to disease. So now I'm going to take some time just to talk about a couple of novel or new areas of research regarding skeletal muscle metabolism and environmental stressors. First and foremost, we'll talk about pollution, as this is kind of a global crisis and something that now you guys can link to how it might affect actual skeletal muscle and link to this course. So this study, looking at skeletal muscle mass and how it's influenced by pollution. So this study is out of Taiwan, and it measured body composition of older adults between October 2015 and November 2016. And what they found, or what they measured, was a link between body composition and air pollution in the areas of Taiwan that these people lived. What they found was a correlation between long-term air pollution exposure, so the higher the air pollution, the lower the skeletal muscle mass of these people living there. Of course, if they had a reduction in skeletal muscle mass, it was also accompanied by a concomitant increase in fat mass. However, what they did find, and a kind of silver lining to the study, was that individuals who were physically active had mitigated the response that this pollution caused. So if you were more physically active, you would have less declines in skeletal muscle mass and less increases in fat mass than those who were sedentary. So again, this is a link between, it's correlational, but it's a link between air pollution and reductions in skeletal muscle mass. Next, I want to talk about what perhaps the most common link between air pollution and skeletal muscle metabolism, but really this idea of how pollution influences insulin resistance. So what this study did was it looked at mice, and they provided them with clean air for 10 months or another group with air pollution or polluted air for 10 months. They then performed glucose tolerance tests to look at insulin sensitivity or insulin resistance in these mice. What they found was that the mice exposed to air pollution had higher insulin resistance, or they demonstrated insulin resistance compared to the mice in a clean air condition. So on this figure here, the black triangles are the pollution group and the open circles are the clean air group. So really this provides a link to air pollution and a possible tie-in to insulin resistance. And what these authors also found was that this insulin resistance linked to pollution was also related to decreased mitochondrial content. Interestingly, this has been shown multiple times with different pollutants, whether it is air pollution like smog or coating the rodents' foods with pesticides and ingestion of those pesticides. All scenarios, we see an increase in insulin resistance following exposure to pollution. Next, I want to talk about brown adipose tissue and how pollution might influence brown adipose tissue. So there's actually evidence that exists that supports a link between exposure to pollution and obesity. So what this study did to kind of assess that or contribute to these findings was looking at rodents that were fed a normal diet or a diet that was coated with DDT, which is a pesticide. And what they found was that the rodents that were exposed to DDT or a pesticide had significant reductions in energy expenditure compared to the control diet animals. And with the figure on the right here, what I'm showing you is that it was linked to a reduced ability for non-shivering thermogenesis through brown adipose tissue. So these are just markers, mRNA markers for brown adipose tissue. Again, you see these dramatic reductions in these animals that were exposed to pesticides throughout their food, throughout their life. Now I just want to talk about gravity for a little bit before our last topic, which is circadian rhythms. So you guys probably know and you've heard that exposure to gravity results in significant skeletal muscle atrophy. So now I just want to show you some literature that supports that. So this study, again, really cool because they actually followed 9 individuals who were crew members for the International Space Station. They followed them prior to and after a prolonged space flight of about 180 days. What they did was they took biopsies at baseline and upon return back to Earth from the gas rocks and the soleus. And we know that exposure to outer space or space flight results in prolonged weightlessness, whereas walking on Earth, obviously we have gravitational forces acting upon us. So this prolonged weightlessness of spaceflight actually produced substantial losses in skeletal muscle fiber mass, force production, and power from those muscles. Interestingly, the greatest atrophy was actually seen in type 1 fibers, so a 20% atrophy of the soleus was seen, and peak force declined about 25% from that soleus as well. This is interesting because when they send these astronauts into space, they actually have countermeasures or exercise training programs in place for them. So we still see this severe atrophy despite those countermeasures in place. And what this study kind of addressed and highlighted is this idea that we need new high intensity exercise programs for these astronauts to mitigate the severe skeletal muscle atrophy that is obtained through spaceflight. And it really shows us that walking around on Earth with gravitational forces acting on us is a way to provide a stimulus for muscle growth that we kind of don't appreciate on a day-to-day basis. So what about fiber type shifting? Do we see that in outer space? So again, same kind of study, 9 members of that International Space Station crew. What they looked at was skeletal muscle biopsies prior to and after that 180 days of spaceflight. And what they saw was that there was about a 12 to 17% shift in skeletal muscle fiber type in the soleus and gastrocnemius, so shifting away from these slow twitch fibers towards fast twitch fibers. So this figure on the right here is just showing you gastrocs and soleus, and again, this idea that black is pre and white is post. We're seeing post spaceflight a shift away from type 1 fibers and a shift toward type 2 glycolytic fibers. So how is substrate utilization influenced in spaceflight or post-spaceflight? Really in conjunction with the shift from slow to fast muscle fiber types, a few studies have shown that there's also an increased reliance on glycolytic metabolism following spaceflight. So basically what this study did was it was performed in rodents, and what they found was that 9 days of zero gravity resulted in this reduction in the ability to oxidize long-chain fatty acids. So decreased ability to rely on fat for fuel, and that was about a 37% reduction, so pretty dramatic. Moreover, other evidence has shown us that unloading of the soleus muscle in rodents, so unloading is another tool that is commonly used to simulate spaceflight or weightlessness. What it did was it resulted in a significant increase in insulin-stimulated glucose uptake compared to the normal weight-bearing soleus muscle. So despite atrophy, we actually have an increase in glycogen synthesis in the unloaded muscle. So again, kind of shifting and showing us that there's this increased reliance on glycolytic metabolism in response to spaceflight or unloading or weightlessness. So now our final topic, circadian rhythms. Just a quick couple tidbits on this, as it is a very new field of research and there's not much out there yet. So what is a circadian rhythm? You guys have probably heard of this before. It's based on a natural 24-hour internal clock. So any biological process that kind of displays this endogenous and trainable oscillation, it's typically called a circadian rhythm, or if it's specifically 24 hours, it can also be called a diurnal rhythm. Some common circadian rhythms that you guys might be familiar with are sleep-wake cycles, feeding patterns, and shifts in core temperature. Of course, we are going to discuss circadian rhythms in the context of skeletal muscle metabolism, and again, really most of this work has emerged in the last 5 years, so there's not a crazy amount to talk about so far. When we talk about circadian rhythms, we talk about clock proteins. So what a clock protein is a circadian locomotor output cycles kaput. It's an acronym. And what they are their genes encoding transcription factors that affects or drives circadian rhythms. So when we discuss clock proteins and circadian rhythms, we'll often see clock or BMAL1 knockout or knockdown rodents as a tool to study them. If you guys look into this yourselves, you might also see PER and CRY as other clock proteins that are manipulated. So here I just want to show you that food intake or regulation of food intake follows a circadian rhythm. We know feeding is critical for animals. We obviously need to eat, and it's regulated by a circadian rhythm. So whether that is metabolic hormones, nutrients, etc., they all have rhythmic cues, meaning they rise, they fall throughout a 24-hour period. We know that the brain and peripheral organs, whether that's skeletal muscle, they can be synchronized, so they can be linked. We've learned about that in the GHRELIN and leptin lecture. And something that's important to note is that mistimed eating or skipping meals, shift work, that kind of thing can actually have negative consequences on metabolic health. So this figure on the right here, you guys don't need to know this obviously, but it's just showing you how complex the integration between peripheral and central organs is in terms of circadian rhythmicity. So we see that there's rhythmicity in terms of hormonal inputs, whether that's ghrelin, leptin, insulin, nutrients, whether that's glucose, fatty acids, ketones, behavior, so feeding pattern cycles, anticipation of meals, etc. So now I want to give you guys an example of the regulation of food intake as it pertains to ghrelin. Remember, ghrelin is our hunger hormone, and ghrelin levels are actually highest in the evening for healthy individuals and lowest in the morning. So that's true whether we're fasting or postprandial. We can see that in the figure for active ghrelin here on the right-hand side. So we see black would be in the evening and white would be in the morning. So black bars are always higher than the white bars, meaning ghrelin levels in the active form are highest in the evening compared to the morning in healthy individuals. There's other research out there that suggests that circadian misalignment, so 12-hour behavioral shifts, so if you suddenly decided you were going to operate on a different clock in the sense that you wake up at 7 p.m. and go to bed at 7 a.m., then we would have an increased postprandial active ghrelin levels, meaning that you have increased circulating ghrelin if you are, for example, a shift worker. And this could actually contribute to the idea of overeating or obesity in the sense that ghrelin is hunger hormone. If the levels are increased, perhaps we can have a scenario of overeating or obesity. What about actual metabolic regulation for skeletal muscle? So considering lipid metabolism and circadian rhythms, this study had 12 healthy males. They took 5 skeletal muscle biopsies over a 24-hour period. So 8 a.m., 1 p.m., 6 p.m., 11 p.m., and 4 a.m. What they found was that lipid metabolism follows a circadian rhythm as well, meaning that skeletal muscle oxidative capacity was actually highest at 11 o'clock p.m. at night and lowest at 1 o'clock p.m., where glycolytic metabolism perhaps is highest during this 1 p.m. phase. What they also found was that there was an association with changes in mRNA expression of these clock proteins that followed these same trends. So clock proteins were lowest at 1 p.m., highest at 11 p.m., suggesting that there's this link between the expression of clock proteins and lipid metabolism, linking circadian rhythms and lipid metabolism. So now, one of the last things I want to talk about is the idea of circadian rhythms and insulin resistance. So this study actually took muscle cells from mice, so C2, C12 myoblasts, and what they did was they silenced or knocked down clock proteins, clock and BMAL1. What they did was that once they silenced these clock proteins, they assessed glucose uptake and insulin signaling. What they found was that insulin-stimulated glucose uptake was impaired with the mice with the knockdown of the clock proteins, suggesting a role for clock proteins or circadian rhythms in controlling insulin sensitivity. So if we look at the figure on the right here, we see that insulin-stimulated glucose uptake, so phosphorylation of the insulin receptor, phosphorylation of AKT, these are classic markers of insulin-stimulated glucose uptake. We see they're dramatically reduced when we knock down clock proteins, meaning if they're reduced, we have insulin resistance or an inability to respond to insulin-stimulated glucose uptake. Moreover, what they also did was they found in normal mouse myoblasts that the induction of insulin resistance through the delivery of hypalmitate, so they actually gave these mice cells hypalmitate to induce insulin resistance, and they found it was actually correlated with a downregulation of these clock proteins, clock and BMAL1. Again, showing us this link between the clock proteins and insulin sensitivity. So if we induce insulin resistance, we actually downregulate these clock proteins as well. Lastly, putting it all together, what does this actually mean in the real world? Shift workers are the classic example of disrupting circadian rhythms. We know shift work is accompanied by a greater prevalence of disease, whether that is cardiovascular, metabolic, GI, or sleep disorders. What the study actually did was they put shift work, they simulated 4 nights of shift work in human individuals who normally don't do shift work, and they compared it to a normal day shift scenario. So on this figure on the right here, we see that the day shift is the white bars and the night shift simulation is the gray bars. And what they found was they looked at glucose infusion rates, so insulin sensitivity, prior to the 4 days of day shift life or prior to the 4 days of night shift life, as well as after the day shift life or after that night shift life. And what they found was that working the night shift increased the fasting plasma glucose as well as decreased insulin sensitivity. So through this euglycemic hypoinsulinemic clamp, they found that infusion of glucose was lower compared to the day shift work, meaning that there was a reduction in insulin sensitivity or an increase in insulin resistance for these individuals who were put on a 4-day simulation of a night shift, which suggests in the long term that shift workers may be at an increased risk for developing insulin resistance and progressing towards type 2 diabetes. So up next, on Thursday, I'll be connecting with the individuals presenting on ergogenic aids. And next week, on Thursday, I will be posting an exam review online. Stay tuned for an announcement regarding submission of exam review questions. And for those who need your participation mark, that's specifically targeted to you guys too.